Hello, I hope everyone is fine. I'm Leandro, and this is a joint work with Professors Marcia Cerioli and Petrucio Viana. First of all, thanks the organizers for having us here and for making this event possible. We know how hard it can be to keep things working from the distance, but you guys have been doing a great job. Congrats. I just hope that the internet connection is not gonna let us down during the event and everything's gonna be okay. Well, I'm going to show you a natural deduction system for the logic of binary relations, which is a formalism based on the calculus of binary relations, which was firstly introduced and hugely developed by these guys here. This was done in the context of formalizing logic and putting logic in this mathematical and algebraic framework. But in modern terms, we can take the calculus of binary relations to be just the set of valid equations for the algebra of binary relations, considering these operations here. So take, for instance, this structure where the domain is the set of all binary relations on a given set U, closed by these very well-known operations of union, composition, complementation, reversion, these constants to be the universal relation and identity relation. Here we got some valid equations for this algebra, but of course there are infinitely many others. So this is just to say that we are taking the calculus of binary relations to be this set of valid equations for this kind of algebra. Okay. Well, in the end of 30s, in the beginning of the 40s, Tarski was very enthusiastic with this algebraic approach to logic, and he raised the question if this calculus could be axiomatized, in the sense that if there could be a set of equations from which all the true equations of the algebra of relations could be derived. Well, lots of work was done here by different people, and the answer is yes, it can be axiomatized, but not by a finite set of equations, not by a set of equations using a finite number of variables. And to get things even worse, for every natural number k, there is an equation in the set of axioms containing more than k distinctive variables and all the operators. So as you can see, these results show that any axiomatization for the calculus of binary relation within this framework is going to be very complex, very complicated. And the examples that we have in the literature confirm that. This is the kind of axiom system that no one would be happy to work with, for sure. So given this situation, some people have tried different approaches in order to provide a complete and at the same time a simple framework for this calculus. And here is where our natural deduction system gets in. But before showing our system, since Wadge had already introduced a natural deduction system for the same calculus, we think it's convenient to compare our system to his. Well, it seems that there is no generally accepted definition of what a natural deduction system is, but Pelletier points out 9 aspects that, in certain sense, qualify a formal system to be entitled as a natural deduction system, and also classify different kinds of natural deduction systems. He points out 9 aspects, but I'm going to use just 3 of them to compare our system to Wadge's. The first one is how closely the system is to embrace the introduction and elimination idea of Gensing. That there be an introduction rule and an elimination rule for each connective, and that there be no other rules. In Wadge's system, we see a pair of rules which is not introducing and nor eliminating operators. In our system, we try to avoid this kind of rules. In our system, all the rules but one, which is inevitable as we're going to show you. So all the rules are introduction and elimination rules for operators. This is the first difference. The second is about the kind of basic items or data structures on which inference rules are defined. In our system, we define the inference rules on sequence, while Wadge has inference rules defined on formulas and on this kind of generic sequence. Well, he doesn't say it's a sequence. Actually, he doesn't say anything. He just showed the rules in a very informal way, but he's definitely defining some inference rules in different basic items, because we can see formulas and we can see this kind of generic sequence. And this is a very unusual aspect of a natural deduction system. The third aspect that we can point to be different in our system and Wade's is the format of proof representation. In our system, we define proofs as trees. And in Wadge systems, again, he doesn't give the formal definition of proof. His presentation is quite informal. But since he has different rules for different data structures, we don't know if we can unify a formal format of proof representation in his system. And we cannot say much about that because, as I said, he doesn't present it in a very formal way. Okay, I'm not trying to say that Wadge system is bad or wrong and our system is good or better than his. No, on the contrary, the core of Wadge system is present in our system as well. We just think that as nice as Wadge system is, it does deserve a better presentation and a formally and properly natural deduction presentation. And that's what we are trying to do here with our system. Okay, so let's see our natural deduction system that we call W in honor of this pioneer work of Wadge. Regarding syntax, we define terms in this way. We have all these relational terms, relational variable, the constants, and operation and the operators defined in a recursive way. And formulas are sequence of symbols like this, x, t, y, where x and y are individual variables and t is a term. The semantics of W system is given by a structure with a non-empty domain and an interpretation function. The interpretation function takes the relational variables to binary relations on the domain. And then we have the denotation functions, which extends the interpretation functions to the set of all the terms in a very natural way. As you can see, we are just telling what the operators mean here, all the operations that we have already mentioned for the couples of binary relations. Okay. So this is how we interpret the terms, but we have to interpret the formulas, and to interpret the formulas we need the assignment function, which takes the individual variables to the elements of the domain, and then we can define the satisfiability relation between structure and assignment function and formula in this usual way. Yeah, and structure and assignment function satisfy a formula x, t, y if the pair of individuals denoted by x and y belongs to the binary relations denoted by t. Okay, I think this is a very natural way of defining the semantics. A W formula phi is a semantic consequence of a set of formulas gamma if we use here again the very usual definition of semantical consequence. Okay, now we can go to the mechanism of inference. As we said, the data structure of W are sequence that we denote in this way. The W proof trees are trees whose nodes are W sequence and whose edges are labeled with tree labels. And the labels are just the name of the inference rules applied in the proofs. Okay, and the trees are defined inductively by the rules of proof constructions that we are going to show you in a minute. So a proof in our system is just a W proof tree pi such that the sequence is in the root. Okay, now we can show you the rules of proof construction, and here's the only rule that is not an introduction and elimination rule of sequence. Of operators. Okay, we need this rule because without this rule we can't even start a proof. So I'm gonna show just some rules just for you to get the idea. We don't have time to show all the rules, but here we go. If this is a tree proof, if this is a proof tree, and if this is a proof tree, then this guy here is going to be a proof tree. You can see that we are applying an introduction rule for this operator in the sequence. Yeah. Here, how we eliminate this operator in the sequence. And we represent all of our inference rules in this way. It's not only an inference rule, but it's also a proof construction rule. Yeah, because in this way we are not only telling how to infer sequence, but how to construct proofs. Okay, here's the elimination rule for this Boolean sum. And yeah, I think you got the idea. These rules of proof tree construction could be presented in a concise way as inference rules on sequence. Here we have all the other rules. And this is how our system works. Well, back to the problem of providing a complete system for the calculus of binary relations. Since our system doesn't have equations, the way that we prove equations in our system is if you have a valid equation for the algebra of binary relations T1 equals T2 in T2, sorry, some Portuguese came in the mind, T1 equals T2, then you can, in our system, the way of proving this equation is just proving these two sequence here. Okay, and that's it. I'll finish just quoting Pelletier. I'm gonna read just in case someone is just listening and doesn't have the video. There are no clear and unequivocal criteria according to which we can always label a logical system as natural deduction. There is instead a set of characteristics that the system can have to a greater or lesser degree, and the more of them that a system has, the more happily it wears the title of natural deduction. That's it. Thank you. Since this has been recorded, I guess that now we're going to turn to a live section so I can answer the question if there is any.